recording. So welcome. Let me find a mouse. There we go. And we're going to go from current slide. There we go. Okay. So we're talking about apparent weight. All we're doing for this class and for last class and for next class is we're using Newton's laws in different ways. So there's this thing called apparent weight, and you might have noticed it. If you've got an elevator ride, especially an elevator that goes quickly. Like when I came across to the States in '79, I went up the Old World Trade Center buildings, and they're like a quarter of a mile high. And you can get the express elevator, well, you could get the express elevator that takes you from the bottom to the top in one shot. So you can go to the observation towers, I think. I don't think there was a break in between. And when you got into that elevator, it actually got to quite a speed. And you could literally feel it in your knees when you were starting off. You'd feel your knees kind of flex a little bit. And then when you got to the top and you slowed down, you'd feel yourself rise a little bit. Well, imagine that you've been fishing and you catch a fish and you're proud of it, so you have it hanging on the little mass balance, the little spring balance thing. And you read it and it says, like, I don't know, 40 newtons. And when you get in the elevator, what you'll notice is that when you first start off, it will seem to weigh more than 40 newtons for a split second. And then when you're just going at constant speed, it's back to 40 newtons. And then when you get near the top, it'll read less than 40 newtons until you stop. And then it's 40 newtons. And if you're going down, when you first get in, it'll read 40 newtons. Then when you press the down button, you start going downwards, then it'll read less than 40 newtons. And then when you get to the bottom, it will read more than 40 newtons, and then it'll stop and it reads 40 newtons. So the weight is changing depending upon your motion. And you can remember all that, or you can just use a diagram and you can use Newton's laws. So we say if it's stationary, then what we have is we have the mass of our fish and we have a tension force in the string. So there's a few things you don't really think about. The spring balance does not know there's a fish there. It just knows that there's a force in the wire, in the hook. That's all it knows. So the weight equals the tension. And if we have a apparent change in weight, we call it the apparent weight equals the tension. Whatever the tension reads is what we're going to think the weight is. And the tension, of course, is a action-reaction pair, so the tension is also the thing that's pulling the fish up, but we also have the weight of the fish, mg. And if we got zero acceleration, that's all we've got. But if we have an acceleration taking place, then our diagram needs to be modified slightly. And we need to take into account the acceleration. And maybe the acceleration's up, or maybe the acceleration's down, depending upon our motion. But we've got to take now into account that acceleration. So we say the scale proves a tension force, provides a tension force needed to match the weight of the mass. So it's equal and opposite. The scale provides a tension force needed to match the weight of the mass and also causes acceleration. And that's what we're going to practice today. So we say, here's a 4 kilogram object. Just draw it as a 4 kilogram object. It hangs from a force gauge, so let's put it onto a force gauge. It's traveling in an elevator, so there's going to be an upwards tension, which is holding the 4 kilogram fish up, and there's a downwards tension, which is pulling on the force gauge. And of course, there's a weight, that's mg, which is 40 newtons. We know that that's 40 newtons. And then it says it's traveling in an elevator while moving upwards and speeding up. See, there's the significant language. Moving upwards and speeding up. Moving upwards means I'm going in that direction. There's my v. Which direction does my acceleration point if I am moving upwards and speeding up? Yeah, that's exactly right. Think back about your physics in previous chapters. if the velocity and the acceleration are in the same direction, you're speeding up. And if your velocity and your acceleration are in opposite directions, you're slowing down. Remember that? So if I'm moving upwards and speeding up, my acceleration must be in the same direction as my velocity. So my acceleration is upwards in this case. And what I say is, there's acceleration, so the sum of the forces equals ma. Now, you know, I got to pick an object for this to work. It's just magically on the page. I got to pick an object to apply the sum of the forces on. So I say, okay, I'm going to pick an object. I'm going to pick my 4 kilogram mass. And I say, oh, resolve my forces vertically around the 4 kilogram mass. So I say plus t, because that's pointing upwards, added to minus 40, because that's pointing downwards, is equal to the mass, oh, shouldn't have done that, 4 times my acceleration. And I look at my acceleration, it's 3 meters per second squared. But it's positive, it's pointing upwards. So that's going to be plus 3 meters per second squared. So can you see, that's what we've been doing all along, you know? When we did our dynamics, we picked one or other of the masses, and we said the sum of the forces equals ma for this mass. And when we couldn't solve the answer, we'd say, oh, well, the sum of the forces for the system equals this mass times acceleration. So we're just doing the same technique. The diagram's different. We're just applying it in a different circumstance. So we say t is equal to 4 times 3 minus 40. I'm going to bring that to the other side. That minus becomes a plus. So we get t is equal to 12 plus 40, which equals 52 newtons. So it seems its apparent weight, the conceptual bit is you have to know that your apparent weight is whatever your tension's reading. The apparent weight is equal to 52 newtons, more than it would be if you were coasting or if you were stationary, more than it would be. And you could figure it out. You could say, well, the weight is 40, and then I've got to pay for this acceleration, so the acceleration is going to be 3 times 4, which is 12. But then you've got to decide, is it going upwards, is it added to, or is it subtracted from? And people make slips about that. And I don't even worry about that. I don't do any of that in my head. I just draw a diagram, and then I apply Newton's laws. 4 kilogram fish. It's connected to a force gauge. It's traveling upwards in an elevator. Let's just put our tensions in. Let's put our weight. And then I say its acceleration is 3 meters per second. It's traveling upwards while slowing down. So my velocity is upwards, but now I am slowing down. So that's my acceleration, which equals minus 3 meters per second squared, because up is positive and downwards is negative. I say the sum of the forces on the 4 kilogram mass is equal to the mass of the 4 kilogram mass times the acceleration of the 4 kilogram mass, just like we've been doing in the past. I look at my diagram and I go plus t added to minus 40 is equal to 4 times minus 3. So t is equal to minus 12 plus 40. So t is equal to 28 newtons. And again, you know, for me, the math takes care of itself. It just falls out. I'm not learning anything special with this. There's not a special case. I just drew a different diagram. Then I applied Newton's second law like I'm always doing. So can you see how, as if you learn the approach, as long as you can read the words and draw the diagram, you don't have to remember all this stuff. You just have to basically learn how to draw the diagrams and then let the math take care of itself. Cool. And I think that's it. So let's just